in London, and he will talk about surfactant spreading. And then we have a second short talk by Hunter Lopez.
Well, thank you, Ray. So, as the title says, it's all about surfactant spreading, fingering, enhanced spreading. It's joint work with Omar Matar, George, Mark and Barry, the postdoc, and a couple of students. So this is quite a long sort of, it's kind of a story really. So this is about an experiment. So typically done in a Petri dish, so a very small dish, very thin layer of fluid, nanometers thick, or maybe microns thick. So the experiment goes like this. You have this thin fluid layer, and different people use different fluids in different experiments, and we'll talk about that, but let's imagine that it's, I don't know, water for the time being. And it's perfectly clean, there's, it's a lovely fluid layer, perfectly erased. You come along with a pin or a pipette, and you have a drop of exactly the same fluid. The only difference is that the fluid that you're about to emplace, the little droplet you're about to put on there, is loaded up with surfactant. So it's loaded up with a chemical that wants to sit on the surface. You put this droplet gently, you don't throw it down there, you put it gently on the existing thin film, and then you see how it spreads, how this drop spreads. Well, because you've got something there which lowers surface tension. The force which is causing this to spread, it's all so thin, gravity plays no role at all. You've got a surface tension gradient, so you've got a surface force which pulls the drop along. And so the question is, what do you see? And what happens here is rather bizarre. You see that the drop sits there, and at the edge of the drop you get a very, very thin region, and you get a kind of thick crown which kind of moves outwards. And in the thin region you get fingers. And so the question is, why do you get the fingers there instead of somewhere else? Because typically when you do thin films, so those of you who work on thin films, you'll be very familiar with flow down a plane. So the typical problem is you have a plane, you trap some fluid behind it, it's a very thin layer, you pull this away, you can do the experiment in your kitchen with oil or honey or something. The sheet, the interface or the front comes down, it's thickened when you look at the side of it, so it's a kind of capillary ridge, there's a thick bit, and the thick ridge fingers. So the physics is typically that if you in your mind, you take the thick ridge and you take one piece and you make it a little bit thicker, well, there's less viscous drag, so it moves faster. So there's a mechanism for it to move faster. But then, of course, if you look side on, you've got surface tension holding it back. So there's a competing mechanism which gives you the finger size. So typically, thick ridges equals fingers. In this particular example, the thick ridge is completely stable, and it's the thin bit that fingers. So the question is, why does that happen? And after discussing that, we'll talk a little bit about surfactant enhanced spreading. So there are some really interesting problems. When instead of the front, the thing you're tracking, going out as powers of time, t to the quarter, you can do similarity solutions. You can show that they should go out at t to the quarter. They actually go out at t to the 1. They actually go out much, much faster. So I'm going to talk about why that occurs. So that's the kind of the motivation. So the first experiment I talked about is where we drop this little droplet of fluid down and we see what happens. And I'm going to talk about the theory, I'm going to talk about why there's fingering. Oh, and then I'm going to talk about what happens. So there's a technicality to how much surfactant do you put down. So the surfactant are little arrangements of chemicals, and they have a head group and a tail group. And the head group wants to sit. So one piece is hydrophobic and one piece is hydrophilic. So typically the head group loves water, the tail group hates it. So that's why they're attracted to the surface. But if you have enough surfactant there isn't enough surface for them to fit anymore. Sorry?
Yeah, so how big is this graph?
I'll show you some pictures.
Is it like
There we go.
microns?
Yeah, so they don't have signs on. So the film is 120 nanometers thick. These are much more than 120 nanometers. They're millimeters across, probably.
Okay.
About that size. So yes, they are millimeters across. So we're going to use a disparity in the length scales at the moment. We're going to use lubrication theory to get down to thin films. So the technicality I'm going to talk about, or I'm going to obsess about at some later point, is what happens when you have so much chemical that the pieces which are attracted to the interface, there's not enough space for them to fit there anymore. it then becomes energetically favorable for some of them to gang together as a kind of bunch of friends to protect themselves from the evil water. And this kind of ganging together, it's called micelles. And there's something called the critical micelle concentration. So once the concentration goes above a certain amount, they rush to the surface, but there's no more space there, so they kind of gang together. And there's a kind of an effect which, so some of the things which are seen are caused by the fact that you have micelles in the system. Then I'm going to talk about what happens when you do the spreading, but then there's an interaction between maybe the chemical doesn't want to rush to the top, maybe it wants to rush to the bottom. And if it rushes to the bottom, it'll alter the wettability. So it may alter how the fluid, how much the fluid likes the surface over which it is spreading. And that too can have some effect. So we're going to talk about a whole bunch of things. So it's really a kind of a marriage of chemistry and fluid mechanics. So these are typical experiments. These are the ones done by Anne-Marie Casabin, who's at the Collège de France, or was at the Collège de France when she was doing this. I don't know if she's moved on somewhere else, but her and her co-workers, I've only picked out one of their papers, but over about a 5 or 6 year period, they wrote paper after paper after paper, doing more and more and more exotic varieties of this spreading problem. Ethylene glycol, this is its formula. They put down a drop, and depending how much chemical you put in, you see quite different features. Now, in order to try and get an idea of the depth, they used some color coding. So the fact the blue is thin, the orange is thick, the black is this is the drop you've deposited. This is a few seconds after deposition. So a few seconds after deposition, the fat drop pretty much sits there. A very, very thin region has formed around it, and then there's a thickened rim which propagates out. You can't quite see, but you will in the next overhead. There are some very, very fine little fingers in this thin region. Now, as you increase the CMC, as you increase the amount of surfactant, you see that the fat drop, well, the fingers, in fact, kind of come out from the edge. It doesn't thin and then it's in the thin region. It comes out from the edge. And you get some bizarre situation where you seem to get maybe 2 rims with fingers on an inner rim as well. And as you go to the other extreme, you kind of get a fat drop, but there is no thinned region. The fingers seem to come directly out of the side of the drop. So what we wanted to do was we wanted to capture this trend, and more importantly, we wanted to show why there were fingers there at all. Because before we embarked on this particular topic, various people had looked at this, and typically what was being done was that people were looking at a thin film, putting down a monolayer of surfactant. In that case, you got the thickened rim, you got a bit of the thinning, but you never got, when they did those simulations, they never got fingering in the right place, no matter how much they tried. They tried all sorts of tricks. And the best thing that happened was you got what's called transient growth. So you could get a little bit of instability for a while, but then it would die away. And so there were various papers which had the view that there was some strong nonlinear event which was happening, but it turned out to be false. And that this is, in fact, a linear stability problem.
Are those drops on a fluid base or on a hydro?
This is all the fluid problem. So this is back to my Petri dish. If your Petri dish is got 120 nanometers thick, you come along, it's pre-existing fluid, it's definitely there. You come along, drop your little drop down, observe, take pictures. What was nice about Anne-Marie Casabin's work was that she showed something quite viscous, and these were all quite slow, and so she could really kind of observe what was going on. The experiments on water tended to be much faster and a bit messier, and in the sense that it wasn't so easy to. It just wasn't. It would just happen much faster, and I think these were much clearer set of experiments from my point of view.
And the surfaces were smooth to the micro scale.
Yeah, so she did this wonderful thing where she put it, in order to get the layer this thick, she spanned them, or her and her students, I think they spanned them, so they spin coated them to this beautiful kind of perfect 120 nanometers.
Were they doing it on a cleave?
No, yes, they were. They were doing, I can't remember, it was mica. I think it was the mica. So they're professional chemists. They were doing a very, very professional job. Stunningly so, in fact, from my point of view.
So in the upper right, there's the
big
phenomenon that I want to get to, but even if you don't, I just think that it might be interesting that some of them are longer, his fingers are longer, and they have kind of a thumb on the end.
You will see, George, how far forward do you want me to jump on my dog? So these are some zoom-ins. So as I say, Anne-Marie Casabal was not the only person. There were a whole bundle of other people who did these experiments. And in fact, they go back to the 1980s. Sandra Troyan, there's a group that was at Princeton, but I think she's now at Caltech. There's a large group of people doing that. There was a bunch of people at Imperial. This is Luckham, Omar Matar, and my colleagues were doing experiments as well. There are many other people. I don't wish to omit people, but there were a large number of people doing experiments. This is a zoom in of one of the figures I showed you earlier. This is the fat drop. This is the thinned region. This is the thickened ridge. Thickened ridge, stable as a rock. Thinned region, obviously got some instability, little fingers in there. As you increase the concentration of chemical, you see that the kind of directly, obviously thinned bit has gone away, and you've kind of got a skirt where the fingers come out from the skirt. You've got the thickened region thick as a rock, sort of stable. As you bump up the concentration even further, your thinned region seems to get very large, and what happens is you seem to get two fronts. You've got the thickened front, which is in fact off the edge of this photograph. Then it kind of goes down. You've got the thinned region. Then you get a second thickened region, which has fingers on it. Then you have another really, really thinned region, which seems to be so thin that it's starting to de-wet. So this is the pattern that I'm assuming is de-wetting. This is a picture from a different group. I'm basically showing you that these experiments are kind of reproducible in trend. So this is the one from Troyan and the group in Princeton. So this is the thickened ridge. In this particular example, they've taken a photograph quite early on. And in fact, it's not stable early on. It's just a little bit unstable. And this is what deceived people into thinking that it was some nonlinear event which was causing this. And that somehow this initial little bit of instability was somehow feeding into some nonlinear process which then gave these, which is not true. Anyway, so this is the thickened front which is propagating outward, a little bit of instability to start with. This is the thinned region leading into the fat drop. But in the thinned region, you've now got a little thick bit on which fingers are formed, a thin bit, and a really, really thin bit in which it's now de-wetting. So I'm going to show, in fact, the theory I'm going to produce is going to produce all these things. And so we'll be able to see it. So this is what I mean. So this is the thickened front, completely stable. It turns out that when you look at things at very early times, it's not quite stable. So these are a small instability in the thickened front.
Well, what is dark versus purple?
So these were color coded for a gallery for the physics of fluids by this grouping. So this is an artistic. These actually mean something in their coloring. These are for a gallery of of physics of fluids. So but from experience, yeah, of course. I mean, I can tell you. So I can interpret from my knowledge of these things exactly what's going on here. This is the thickened ridge. This is at a relatively early time, so it appears slightly unstable. This is all the thinned region, and the fat drop is down here. When the chemical concentration is high enough, the thinned region stretches right out, and you've got a little thickened region, which is this one. This little thick front is itself unstable and has the fingers on it. This is stable, and this is de-wetting. That's what's happening in that picture. And we will see a simulation which generates pretty much this later on. Well, so the effect of surface wettability can be kind of quite strange. So what you can do is you can do this experiment, and if you choose your chemical right, what happens is you get your fat drop, you get your thinned region, you get the thickened front propagating outwards. But when enough of the chemical has absorbed onto the base, it makes the base hydrophobic. And so what happens then is it spreads out and then retracts back in again. So you can manufacture your drop to do really quite odd things. So this is something called autophobing. So you can these are taken from these experiments by my colleagues in the chemical engineering department. And this is an example of autofocus. So this is what happens when the surfactant doesn't necessarily rush to the top, but it's also got a preference for going to the bottom. And when it goes there, it'll alter the wettability at the base. There's also a bunch of surfactants which are called trisiloxane. And these trisiloxane surfactants lead to an effect called superspreading. And so what happens is you can show that if you put down a monolayer of surfactant, you can show that the radius goes like t to some power. And you can pick out those powers using similarity variables. Now, it turns out that when you put down some surfactants, they don't go like the powers that you predict. In fact, they go way, way faster. And they're called superspreaders, and we will come to that later as well. I guess I'm trying to show you a kind of zoology of different effects that happen and that we would like to have a model for. So this turns out to be pretty important in a whole variety of different settings. In the industrial coating flows, there's a really nice biomedical one called surfactant replacement therapy, which Oliver Jensen worked on. For those of you who know Oliver, I guess Tim, he was your student, right? So worked very widely on. There are applications in microfluidics. There are lots of places where you're simultaneously doing chemistry in the sense that you're transporting things around which affect the surface tension. It can be something simple like soap. It can be almost anything you're doing. And when you look at things on a micro scale, clean fluids are actually quite rare. It's actually dirty fluids which are much more common. So the mechanism for fingering was a long-standing problem, so as was the mechanism for super spreading. So I'm going to address both of those in this talk. Lots and lots of experiments. It's kind of a difficult literature to read as a mathematician or a physicist because you're reading chemistry. And the things that are important to a chemist are not necessarily the things that are important to a mathematician. So you're sort of looking at a kind of experimental zoology of trends, but it's often hard to pick out exactly what's going on. You've got different experimental groups using different fluids, and so they're not necessarily fixing everything and only varying one. They may be fixing 2 or 3 things, but varying 3 or 4 things simultaneously. So it can be a bit perplexing. But nonetheless, there's a sometimes contradictory picture, but you can pull out pretty much what the trend is. And I've tried to show that in my earlier overhead. Quite a lot of prior modeling, particularly on, let's take a thin film, let's put down a monolayer of insoluble surfactant, so surfactant which only lives at the surface. And there was primarily in connection with this surfactant replacement therapy, Oliver Jensen, Grotberg, a large amount of work on that problem. Various people were interested in the fingering problem and attempted to analyze this in various ways. It's kind of, because it looks a bit like viscous fingering. Lots of people tried to draw analogies with viscous fingering, but it turns out it's nothing to do with viscous fingering. The monolayer itself is resolutely stable because you get the thickened front, and that thickened front turns out to be resolutely stable. So it was rather perplexing as to where on earth this instability came from. But as I say, we'll get to a model and it'll show it to be the case. I worked on this with Omar for a while, and we did the fingering problem. And Oliver Jensen kind of dipped in somewhere in the middle and also did some work on this. Then the super spreaders, there's a large amount of work also, experimental. Again, there's a pretty contradictory picture with various people claiming different spreading rates. It's clear that these surfactants do spread rapidly, but it's pretty hard to get a coherent picture from the chemical literature. But there is a consensus that these surfactants do have very high spreading exponents and the mechanism is very poorly understood. So these are my summaries of what's going on. So I'm actually going to model this. I'm not going to model it as an axisymmetric problem. I'm going to model it as a kind of thickened ridge. I'm going to do a 2-dimensional problem. I'm going to do a thickened ridge, take a section through it. I'm not going to bother with axisymmetry for the time being, because I really want to understand the mechanism of the fingering. And if you go back to something like this, I'd say the curvature is actually playing an irrelevant role, and actually all I care about is taking a section through like this, in which case I may as well do a 2-dimensional problem. It's easier to do the numerics and so on for a 2-dimensional problem. We've done the axisymmetric cases, but they don't show you anything new. If we take a section through this, we've got our initial film that we place our fluid on. I've called it the precursor, but it's not some game to get over contact lines. It's got a genuine depth. There's the big fat drop we put down. There's a typical kind of length scale. Maybe it's the initial radius of the drop, but this length scale is much larger than this. So there's a kind of convenient ratio, which is epsilon, which is the ratio of the depth to the length. And because this is conveniently small, this leads us to a nice asymptotic representation of what's going on. So the other things which are of note are that there's something called a spreading pressure. So you can work out that there's a characteristic velocity. So the key thing is that you've got chemical concentration, which I'm going to call chemical concentration at the interface, which I'm going to call gamma. And there's surface tension, which I'm going to call sigma. This is a process of non-dimensionalization, and that is that the surface tension, the key thing is the difference between the maximum and the minimum surface tensions which are possible given that chemical, and that leads you to the definition of something called a spreading pressure. It's not really a pressure because you have to non-dimensionalize by it. You have to introduce a length, but this is the key thing. Using this, you can work out that there's a characteristic velocity. And now you've got characteristic scales for everything, you can non-dimensionalize the problem. So the way to think about the problem is that you've got the big fat drop, and it's got some surfactants. These are the surfactants. The head group likes the water, tail group hates it. They live on the interface. They lower the surface tension. So surface tension is high here, low there. There's a surface tension gradient, pulls the drop out. Inside here, if the concentration is high enough, the micelles want to link up with their buddies and protect them, and they want to protect the tails from the water. And so if the concentration is high enough, you have a reservoir of chemical which is locked into these micelles in the main drop. As you see, you've got this surface force which is trying to move, really wants to transport these guys from here to there. But because of conservation of mass, as it tries to do this flow, you get a thinned region here. And then you get this thickened front. So you've got this thick region, which does have some surfactant on it. Behind it, you've got the thin region. There is surfactant here. And then you've got this big drop. So what you've got is a kind of mobility problem. You've got something highly mobile trying to go through a little bottleneck. And it's this little bottleneck where it's really turns out to be really unstable. And I guess when you think of it this way, it's not surprising that it's unstable and you get fingers there. Sorry?
Velocity.
Oh, viscosity. Sorry,
So viscosity matters.
yeah. So I'm sorry, I'm not deliberately glossing over things here. But yeah, usually
I have a quick question. I mean, are you distinguishing between concentration on the surface and concentration?
Oh yeah, will do. Absolutely.
I don't want to anticipate.
Yeah. So what I'm going to do is I'm going to write down a complicated-ish model, and then I'm going to simplify it. I'm going to have a complicated model where I'm going to have surfactant on the surface, monomers in the bulk, and micelles in the bulk. And there's going to be, these guys will break up into those who will then go there, or these guys will leave the interface, become those, and then those. So, in fact, next overhead. Thank you. So we have to do a little bit of chemistry. So the little bit of chemistry goes like this. I have those monomers, that head group and that tail group. And if they live on the surface, I'm going to call that concentration gamma. And we could think about this like a chemical reaction. There's a reaction which says, if I have a space at the surface and a monomer in the bulk, it will go to become a monomer sitting on the surface at some rate. A monomer sitting at the surface will leave and join the ones inside the fluid. It will then leave a space behind it, and that will also happen at a rate. The rates at which these happen correspond to whether a surfactant is soluble or insoluble. Obviously, the easiest thing is to say is that my surfactant never goes into the bulk at all and it's completely insoluble. We can also play a similar game with these micelles, this kind of gang of buddies who want to hang around and protect themselves from the fluid. We can say that there are n of these monomers floating around on their own will go at some rate to create a micelle, and a micelle will break up into n of those, and this will happen at some rate. We can use this bit of chemistry together with the law of mass action, which is basically That's like a two-line calculation that you learn when you do a little bit of chemistry or mathematical biology. It's one of these typical things that they use. You can use this to find fluxes. And so we can now find the fluxes from one species to another. So then you can write down PDEs which say, I have a PDE for micelles, and there's a flux of micelles into monomers, there's a flux of monomers into micelles or into the surface, and you can build chemistry into the fluid mechanics. So if we were to write down the full set of equations, they look a bit nasty. So we kick off and we say, okay, incompressible fluid mechanics, Navier-Stokes equations, viscosity, pressure, density. This is the Navier-Stokes equations. This is the mass conservation. This is then going to be coupled to some advection diffusion equations. The surfactant, which lives on the surface, well, we've got to take into account the shape of the surface formally. And so the little subscripts S, these correspond to gradient, to the grad operator locked onto this surface. N is the normal, kappa is the curvature, gamma is the concentration, D is the diffusivity, and these are the fluxes that I just talked about. In the bulk, you'd have an advection diffusion equation for the concentration, you'd have the fluxes into the surface, fluxes into the micelles. Similarly, for the micelles, you'd have an advection diffusion equation, and they break up into these. I don't know if there are chemists in the audience, but if there are, they normally stick their hands up at this moment and say, but you're doing something terrible. You're assuming that there's only one size of the micelles. You're telling me that N is 100 or something. But it could be a whole range of them, or some chemicals will have, several peaks. And this is true. We could in fact make this a poly, we could just put more and more PDEs down here. But that's not really the purpose of this talk. The purpose of this talk is to try to understand the mechanisms of what's going on. And although these look rather complicated, later on we will be able to throw bits and pieces away, and we will get down to a system of nonlinear PDEs, which will in fact be relatively, the word simple is probably not the right word, but solvable. There are some critical things which we need. One thing, when you look at this equation, you think, aha, I know what, I can solve the fluid mechanics on its own, and then these drive what's going on in the chemistry, because it looks like the whole thing is decoupled. But this is unfortunately not the case, because what happens is when this moves around, well, there's a key point, which is that the surface tension gradient couples to the surface stress, and that's coupled into the fluid mechanics. So there is a two-way coupling between the chemistry drives the flow, which moves the chemical around, but then of course because it's moved around, it's changed the force, and so the whole thing is intimately coupled together. So it turns out that the surface tension is really important, and that the surface tension is related to the concentration of chemical at the surface via an equation of state. Now you can make many different choices of equation of state, and this is the particular one that I've chosen. Now Uwe is presumably going to kick up at this point and say that this is not kind of energetically optimal and it doesn't satisfy this, that and the other. But anyway.
And I wanted to ask, do you think there's a relation between the fluxes to and from the surface and the surface tension definition?
Not as it's currently written, no. Not as I've written it.
I mean, that would be sort of my question, whether there should be one.
It's possibly true. And so there are all sorts of issues which this theory I'm going to write down doesn't address. So later on, we're going to assume a kind of vertical isochemistry in that the concentration of micelles across the thickness will be constant. And so, but you can imagine that you might actually have a surface boundary layer in which things are happening. And actually, for what it's worth, I did write down a model with that, but that's not in this talk. And
So in connection with that, equation 02, ds del squared, that's a surface.
that should be S, yeah. I beg
And
your pardon.
now, but it becomes a little more interesting because on 03, I think what you're now telling me is that dB is also going to be effectively a surface one.
No, and then later on, later on we're going to do some. Later on we're going to do a depth averaging.
Well then, sorry, bear with me, but if it's three-dimensional, then there should be a relation between the J's and the dB del square.
Yes, and so that I haven't written that down here, but there is.
Sorry, I must have been interrupted.
No, you feel free. Otherwise, everyone just listens to me, and that would be really dull. So a key thing is how the surface tension and the chemistry are interrelated. And typically one approximation one can make later on is that there is a linear relation between them. That's kind of the first thing to do. That's kind of a detail. But the key thing is that these are fully coupled. So there is another version of this theory, which is a thermal version. So you can imagine that what you could do is you could do a problem where you have a temperature gradient. In fact, Anthony will know this better than me. You can do a temperature version of this, and you take a plate which is hot and cold, or cold and hot. I can't remember which way around now. But the surface tensions of fluids really do care about temperature. But in that particular problem, you kind of come along with kind of godlike ability to fix the temperature, and in that case, these problems do separate out. But in this case, because the chemical can move around, it can affect the surface tension gradient in a coupled way. So these are, in my opinion, a kind of pretty interesting set of equations due to the coupling. So the surface tension, we can look at the pressure is related to the surface tension times the curvature. Then we've got a surface tension gradient, which is the shear related to the shear stress. This is the kinematic condition. We go through these things. I think this is the relation that Anthony just wanted to see. You're always one overhead ahead of me. So this is a relationship between the flux and the concentration of the monomers in the surface. So you've got all these boundary conditions. We're going to assume that the micelles do not absorb at the base, so the micelles don't break up and go to the base. And we're going to assume that the total mass of surfactant is conserved. So these are just consistent boundary conditions with the model. Now we're going to jump about 5 overheads of algebra, and I'm sure you'll be only too happy that I've done this. We can assume that because the thickness is really small relative to the length, there's a small parameter. So we can go into the governing equations and we can take that small parameter, and then we can work out equations for the thickness, which is h. So we end up with an equation for h, the thickness. We end up with an equation for gamma, which is the surface concentration. We end up with an equation for C, which is the concentration of the monomers in the bulk, and for M, where we've taken the fact that the layer is thin and we've done various integrations and so on across it. Now these are, mathematically, I think they're a really nice set of equations, because they look very complicated, probably written as all 4 of them. If we just throw away the monomers and the bulk and the micelles and just look at these two, which are kind of the fundamental coupled equations that you care about. Your H equation, this is basically like a 4th order in H, but it's wildly nonlinear because of the H cubed. This C, this non-dimensional parameter, which is called the capillary number, is normally small. So you've got some really nasty parameters stuck around in here. You've got this gradient of sigma, so you've got this advection term. It's a pretty nasty equation. But then this is coupled, because sigma is a function of gamma, it's coupled in with the gamma equation. But the gamma equation has typically weak diffusivity. In some limit you might say, well, the Peckley number is infinity and this basically drops out, which then leads to shock solutions. So you've got this advection diffusion equation. It's also nastily nonlinear and it's got this flux in there. So these are really quite nasty equations to solve, quite challenging numerically. Very interesting though. So these are the equations we're going to solve. It's a pretty parameter-rich set of equations. So if I was giving a talk to chemists or physicists, they sometimes want to know what exactly are all those parameters. So this overhead is to kill that question. So if anyone's got any questions about any of the parameters, we can read them off here. You're going to have to trust me to pick off what I think are the most sensible ones. So the most sensible ones are things like the ratio of the height of the drop I'm going to put on to the thickness of the pre-existing monomer. R and M is the total mass of surfactant. That basically tells us whether we're above or below the CMC. N is the size of the micelle. C is the capillary number, and the Peckley number. They're primarily the most interesting. But given this range of stuff, you can see there's quite a range of behaviors that you might see coming out of this model. So now we've kind of written down a set of PDEs. But of course, that's only the very beginning of our job. That's not the end of our job at all. It's the very start. So the first thing we do is we say, okay, well, I've got this two-dimensional problem. Let's just look at it. So we have. Let's skip back a bit. So this is our two-dimensional problem. This is our section through the problem. This is x. This is z. But now I've basically filtered z out by taking it to be long and thin. So I really care about x in this direction, and y is the coordinate into the board. Since I want to ultimately look at fingering, I really care about the coordinate into the board. But before dealing with what's going on into the board, I'd better understand that I actually do get shapes like this from my model in just h as a function of x and t. So before embarking on x and y and t, let's figure out what's happening in h as a function of x and t. So I'm going to call that my base state, because later on I'm going to want to perturb away from it. So we're going to have our base state, and then we're going to have perturbations away from it. These are going to be small perturbations, and they're going to be characterized by a wave number k in the y direction. What we're going to care about is we're going to care about whether these perturbations grow, in some sense, as a function of k. And so if they do, we're in business, because we will have shown that we have growing solutions with a particular preferred wave number in that direction, and those will be our fingers. But before really embarking upon that, I'm going to primarily concentrate on the base states, which are functions of x and t. Now, what makes this a particularly kind of awkward problem in terms of linear stability theory is that your base state evolves as a function of time. So typically when you do linear stability problems, you're in the very, very lucky state that your problem is fixed. It's just stationary, and you perturb around some stationary state. Or it's a traveling wave solution. It goes like x minus ct. You can pull out the x minus ct variable and then perturb around the traveling wave. Or you have a similarity solution, and your similarity solution forms the base state. Once again, you can use x over root t or something to collapse your coordinates down, and you can perturb around a known thing. In this case, we are unfortunately in the slightly awkward position where our base state evolves as a function of time. So we have to define what do we mean by growth rate. And so we have to be a bit careful. We use a definition which goes back to some work in turbulence, which is to do with something called transient growth. So what you do is you look at the growth of your perturbation relative to the base state, and then you numerically figure out what the growth rate is, and then you look at that. So we've now got our PDEs, we've got boundary conditions, and now we're going to look at initial conditions. So we're going to come along, we're going to take h to be constant except for a drop, which is this, that we in place. We choose our chemical concentrations so that they are in equilibrium inside the drop. So whatever rules we've got for how the micelles are turning into monomers, are turning into the thing at the surface, they are all sat lovely and cozy in this drop in perfect equilibrium. We put this perfectly equilibrated drop onto the surface, where these f's are basically these are regularized heaviside functions. So we flat, drop, flat. This is a numerical trick just to stop any instabilities in our code. This is the equation that you use given the mass to break things up into monomers, micelles, and whatever. And when we come to do the perturbations, we just take a small value of something multiplied by a Gaussian. And then we see, ultimately, do these perturbations, where do they grow, where do they not grow? So these are the results. So initially, we kick off with a fat drop, which is this. You can see our drop has width 1 to start with, so it's really kind of very, very sharp. It then collapses down, but the drop itself remains pretty much locked in place. You can't see any detail of that, so we've zoomed in on it. This is the drop, this is the thinned region, this is the front propagating out. So it's doing what we can see from the experiment. So this is our base state. It is thankfully doing what we want. This is the insoluble case, so we've thrown out the micelles, thrown out the monomers, simplest possible situation. So then we look to see what happens to the chemical concentration. Well, the chemical concentration remains roughly constant within the drop, but gradually goes down. Along the leading front, it's pretty much linear, and there are some nice scalings which emerge. So the drop itself, it spreads out. I think it's a t to the 1/7. This goes down like t to the 2/7. This goes out like t to the 1/3, if I remember correctly. And these scalings emerge from the work by Oliver Jensen and colleagues that came from the monomer problem. In fact, I've even shown the front position as a function of time versus t to the power 1/3. You can see it locks on beautifully. So this problem is beginning. It picks out the base state picks out everything just as you want. It's looking good.
Insoluble means that it's all on the surface.
All on the surface. Yeah. This is all on the surface. This is the simplest thing to start with. When faced with this enormous set of equations, the natural thing you do is throw half of them away, if you can. See what understanding you have, and then move on from there. So now we come along and we put on these small perturbations with a wave number k. So I've chosen k as 20. The perturbations grow and they lock in to the thinned region. So I mean they're not in place there at the beginning. They naturally grow there. And what's interesting is when you look at the surfactant, you can see that the surfactant this almost looks it goes up and then down again, which will be useful bit of knowledge for later on. This is an evolving problem, so the position of this moves with time, and the position of this peak moves with the thinned region, and so it thins and it exponentially grows, so it does everything that we expect, and this peak is locked to this thinned region, as is the surfactant. This is the surfactant perturbation, this is the height perturbation as a function of time. The peaks of each of these correspond to the thinned points at different times.
So you're solving the linearized equations for H1 and gamma 1 simultaneously with the zero order equation. So there's no quasi-steady assumption or anything.
Absolutely.
Right.
So you could do, so when we first did this, a referee said, quite rightly probably, why are you going through all this pain? Why don't you just freeze? Why don't you just come along with the hand of God and just freeze this at some time and then perturb around that? Which we did do actually. We did that first, as I recall. And you also get pictures like this, but I think it's much more convincing to do what we've actually published, which is do the evolving problem, especially if you have the capability to do them. If you have the capability to do it properly, you may as well. But you could, it would work. You can freeze this and do. I think it's called quasi-steady state something. You can do the freezing, which does also show you an instability.
You get a growth rate out of this?
Yeah, you do.
Is this exponentially growing?
Yep.
Yeah, can you go back one? This pick has k equals 20.
Oh yeah, so you have to make a choice. So when you do this, you choose a wave number.
That's what pick means.
Yeah, sorry, the picture. I'm sorry.
But 20 in what units? Are these in the units of the length of the?
We have to go all the way back to the non-dimensionalization and pull out what 20 means.
It's with respect to L, I bet.
Yeah, I think so too. So for different values of k, you get different. The growth rates vary, and you can actually plot a dispersion curve, which is growth rate. I can't remember what it may in fact be on a later slide, but I can't remember. You can show that there's a preferred wave number, for instance. So in order to verify that linear theory was correct, we did a fully nonlinear simulation. So we took those nonlinear equations and solved them. And we took down, so this is, as I say, this is two-dimensional, so this is a Cartesian problem, not an axisymmetric problem. So we come down and we put down basically a ridge of this with the surfactant on it. We give it a perturbation, in this case, k is 20, and we then set it to run. And we see that we have a fat front, the thickened ridge begins to form. Initially, it's unstable, which is amusing, of course, because when you look at the experiments, of course, initially the experiments are themselves unstable. So these are the little purple things that you were seeing in that original experimental picture. It turns out that the leading front is unstable, but only for a very short period of time, and then it becomes stable again. And then you can in fact see that because the perturbations have forced it to be slightly unstable, but by the time you've got out here, it's as steady as a rock. The thinned region, or the fingers grow into the thinned region, and eventually, and in fact this is coming down to the thing coming out with like a thumb with the bits coming out the side. This is these are the fingers, and you can see that there's some tip splitting occurs. So this is all very reassuring because it shows us that the theory has found fingers in the right place, fingers have the right behavior, the whole thing hangs together. Then we ask ourselves, what's the physical mechanism? Because in some ways that's actually the key thing. We've got a numeric, we've got to start off with the physics, we've turned it into maths, we've abstracted down in the maths to the simplest possible thing we can think of, which gives the fingers. So now we ask ourselves, can we in a mind experiment figure out why it's unstable? So if I take my drop, so I've got my drop, I've got the thin region, and I take a piece of the edge of the drop and I pull it out. What happens when with the hand of, I'm not going to get religious, but the hand of someone, we come along, we pull a piece of the piece out. What's happened is we've increased the surface area there. What we've done by increasing the surface area there is we've messed around with the chemical concentration, and we've created a little surface tension gradient local to that point. That little surface tension gradient pulls more fluid in there and makes that finger grow bigger. Of course, that is balanced by the fact that surface tension itself hates the fact that we've just gone and done this and wants to pull it back. So you have a competition between these two mechanisms, and of course it's the mathematics which figures out which one of these two things is preferred. We can actually verify this by looking at the computations and taking slices across the fingers. So you take the fingers and you take a slice like this. And what you do is you find that indeed, so this is a slice through a finger. So this is a finger. We've gone and chopped it. This is actually this is the high profile. This is the surface tension, the chemical concentration. So the chemical concentration inside the finger is lowered, and so what you can see is inside the little fingers, surface tension is slightly lower, which leads to this little local surface tension gradient drawing more fluid in. And so you can see that this is why your finger wants to grow. But when you look from the top, of course you've also got surface tension, which is trying to stop the fingers growing. And so you've got a competition between these two mechanisms, one wanting it to grow, one wanting it to stop, and that's why you have fingers and why there's a preferred wave number.
So what if you started with just one finger?
You're always jumping ahead of my overhead. Well, I can't. You want this one.
Yeah.
You're going to get these pictures later.
Okay.
Okay. So it looks like the job's done. It looks like we can go to the pub and have some beer and celebrate. But it's not quite right. Because what happens is you see that the minimum is primarily present in experiments above the CMC. There's all sorts of details. Some of the experiments don't have a minimum, and the fingers seem to grow directly out of the side of the drop. At very high CMC, sometimes you get a secondary unstable front. The spreading rates in the experiments are sometimes not the spreading rates that are predicted by this. So now, having found fingers and got a mechanism for it, now's the time to try and refine the theory, to try and catch all the people who stick their hands up and say, you told me that the fingers grow from the minimum, but in my experiment they don't do that at all. Or I've got a front in the middle of my thinned region and it's unstable there, and you told me that the thickened fronts were stable. So now my job now is to remove those questions. So now what happens? Let's do soluble surfactant. Let's have my cells. So the 1, 3, and 5, in the kind of non-scaling, rescaling, the way in which we've done things, M is 1 means that you've basically got insoluble surfactant, 3 means it's pretty soluble, and 5 means you've got lots and lots of micelles. So when it's insoluble, that's the dotted line, you've got the fat drop, you've got the thinned region locked in place, you've got the thickened rim propagating out, beautifully stable. When you've got lots and lots of surfactant there, enough that you're just above the CMC, but you're not really forming micelles, the thickened rim, what happens is the fat drop comes down. There is a thinned region, but there's a kind of fat lump which comes out of the side of the droplet, and then you've got your thickened front propagating off. When you're effectively way above the CMC, your drop is really locked in place. There turns out to be a thinned region with a little front in the middle, then another thinned region, then the leading edge. And so the questions then are, now we do the transient growth problem, where does the instability sit? In fact, if you think back to the experimental photographs I showed you earlier, I showed you pictures where we had a fat drop and we had fingers growing on a skirt which came out of the edge of the drop. And I showed you pictures which had a drop, a really thin region where there was de-wetting, a fat region, where you got fingers, followed by another thin region, followed by the leading front. Let's ignore these. These are chemical concentrations. So, if we use the transient growth theory, what we find is that if M is 1, we get what I've just shown you. Fat drop, thinned region, growth in the thinned region. If we have a fair number of monomers, but we're not really wildly above the CMC, we get a fat drop with a skirt, and the perturbations get locked onto the edge of the skirt. This means that we predict that this lump will be unstable, and we will get fingers here. If we do the problem way above, so we've now got the micelles, we've got the fat drop, we've got the first thin region, we've now got a secondary front, then we've got the leading front. We predict that you get the fingers on the thickened region here, and so this theory predicts that the intermediate lump is unstable, which is exactly what's seen in the experiment. And to answer an earlier question, you can indeed plot growth rates as a function of K and pull this sort of stuff out. You can again do nonlinear simulations.
Oh, what's R?
R's to do with the rates at which things are happening. I've kind of glossed over them. I've kind of glossed over this. This was back in my big list of. This was back here somewhere. So R is to do with the rates. K1 and K2 are the rates. So these are the rates at which I come up with it. I think this governs the rate of micelle breakup. I think. So these are to do with how fast things are happening. Because you've got different time scales. You've got a time scale of spreading, and you've got a chemical time scale as well.
That's why the dispersion relations are different for different R.
Yeah. So this is to do with this is kind of like a chemical time scale versus a physical time scale type of thing. I'm sorry that's a bit vague, but I just can't remember the precise. I remember R being that. So now we do some nonlinear simulations. So this is the case you saw earlier. This is the case where we are heading towards the CMC, slightly above the CMC. We've got the fat drop, we've got the skirt, we've got the fingers growing out the skirt, we've got the leading front. This is the more interesting case where we have the fat drop, a very, very, very thin region. We have a thickened region upon which fingers grow. Then we've got the leading front. So this corresponds to the photographs I was showing where you look from the top, you've got the drop, you've got the thinned region, you've got the fingers. We probably should skip back. That's corresponding to this case. In fact, this is a nice picture because this is way above the CMC. You've got the fat drop down here, you've got the thinned region, you've got the thickened region, you've got the thinned region, you've got the front, which is initially unstable but will eventually become stable. These are the fingers which I'm showing. So these fingers are exactly the ones which I'm showing you here. That's the fat drop, first thinned region, fingers on the thing in the middle. This is the next thinned region, this is the leading front. So that's what you're seeing. Anyway, Anne-Marie Casabat and her colleagues were very generous. They kind of gave us open access to all their data. So it was really kind of very interesting to see. And so what we noticed in some of the experiments when we looked at them was that it wasn't entirely clean, that there were specks of dust, air holes. There were all sorts of things which happened during the experiments. And sometimes things like this air hole would cause such a perturbation that a finger would come directly out the side of the drop and kind of destroy the experiment. But nonetheless, it was kind of an interesting thing. So we then started looking at what happens if you kind of do a big perturbation. What happens to these situations? So we did some experiments like this, where we basically ripped the side of the drop out to see what happened, and we got these beautiful fingers which come out and then they tip split. This is an effect which is very commonly seen in experiments. So this sort of, I guess it's just a pretty picture, but its main purpose was to show that the model was strong enough and robust enough that it could demonstrate tip splitting, which is something which is clearly seen in experiments.
It looks like the number of those bumps is decreasing with time.
Yes, that's possibly true. And you can see that I had to stop the experiment because eventually there was a little numerical instability which I didn't trust. So at this point we stopped. Although nowadays, I could go back, it's probably 5 years ago probably, I could probably go back to these, refine the computations a bit, but I'm not sure.
What about that?
I gave it an initial I gave it a little bit of noise in order to seed the thing. Beg your pardon. So now we come on to, I won't do this for very long, I'm conscious that I'm in fact about to overrun. What happens when you have absorption to the base? So you can have a situation where the surfactant will want to rush to the base. So in those circumstances, what can happen, you can make the model more complicated, you can put in an extra PDE, which is up to the surface surfactant concentration on the base. I haven't written it down, but you can put that in. Then you get, depending on what the rate of absorption is to the base, you can get a situation where a drop, you have your fat drop. Now you've made the pre-existing fluid layer infinitesimally thin. So the leading front morphs into a droplet at the front, which almost detaches from the drop at the back. And it can become like a self-propelling droplet. It can go along at T to the power 1 or T to a much larger power until eventually, so it carries its own little store of surfactant with it. This little store of surfactant that it carries with it kind of detaches, has its own little stock of surfactant, but because the surfactant is going to the base, it creates a little local surface tension gradient specially for itself. And that's enough to keep it going. Eventually it slows down and stops when it's run out of surfactant. So you can see we found T to the 2/3, but some later experiments we did, numerical experiments, we got to T to the 1 by tweaking this basal absorption parameter. So you can, now you have the model, or one has the model with the basic chemistry in, you can adjust that to actually model real things like this. Oh, so this is explaining the mechanism. This is what I just told you, that this basically detaches from the main droplet, and you can figure out that there's a little local surface tension gradient which this carries along with it, and you can find out how fast it grows by tracking this. We've done more work since this picture, mainly by, these were cheating in some sense by having a very, very small, thin, pre-existing layer. And we got very interested in how you did contact lines when you have surfactant. Because contact line is where it truly joins, wet stuff joins dry stuff. But what happens when you've actually got surfactant, you've got something which alters the surface tension at that point? When you cheat and you make it a little clean precursor, does that matter? How do you build surfactant into the contact line? So more recently we've done that, and then we went back to these computations to see whether it made any changes, and it actually turned out not to. So, to conclude, well, there's the family of things which I've attempted to explain. This is the one I like most: fat drop, thinned region, beautiful fine fingers, thickened rim. I guess this is because this is the one we first concentrated on. As we go up the chemical concentration, fat drop, skirt, fingers on the skirt, fat drop, thinned region, thickened region, unstable, and so on. The trends are basically there. I guess we should thank the EPSRC. They were kind enough to give us a platform grant at some stage, up for renewal if the EPSRC are listening. There are some grants. I was in Canada for a while. The Canadians were very kind. They gave us some money as well. The material in this talk is in these some of it's in these review articles, and the more recent stuff on the surfactant enhanced spreading is in this article. Sorry, I'm losing my voice. It's not a deliberate ploy to get out of questions.
So as our next talk is short, we have time for questions.
Okay. If you go back to the place there's only one bump, okay, and if you hadn't seeded this thing with another wave number.
Yeah, I'm not sure what would happen actually.
No, I have this idea. This is what I believe will happen. I believe actually that every maximum in the profile will grow. Sort of like an anti-maximum theorem. And that as it grows, it draws in material from the nearby, and that produces maxima, which then grow. And getting that process might be interesting because you only need a maximum, I think. I don't think you need a wave number oscillation.
Yes, it's possibly true. I think at that time with those numerics, I would have been very wary about doing what you said. I'm much happier to seed it with something and then check that, because what with these numerics we could actually check back with the linear theory, check it was doing all the right things. To do something, I'm not sure. I think I need to go back and refine them because these are actually quite hard computations to do.
I see. It would also be interesting to see if you could continue this in time, whether the two sideband maxima merge with the one in the middle.
Yes. I did put quite considerable effort into trying to take these further and trust what was going on when I went further.
So you trust that tiny little spike on the end of the middle finger?
Yeah, see, that's why I.
Oh, so it's trying to make a singularity even, maybe. Because you would think it'd be burned off by the diffusivity.
Yes.
I come back to my picky issue at the beginning. So how dependent are the results on the nonlinear dependence of surface tension on concentration?
Actually, they're not very good. So a referee, and I'm not going to blame you. Probably not you. I'm just teasing you. But would presumably must have always gone to someone similar to me, and they would always say, "But what about Frumpkin? You've used Schludko, and I want you to use Frumpkin." So every time I would simply just stick I'd put their equation of state in instead of ours, run it, would do, it never changed much. It never did much.
Linear, would this be sufficient?
Oh no, it doesn't. So some things they do care. I can't remember off the top of my head.
So you need some sort of a nonlinear.
Yeah, so you've got to be careful. So the linear equation of state works fine, certainly for insoluble stuff. But you could be very careful with once you go above the CMC, because you need a limit. You can't allow the surfactant. You can't allow the surfactant to carry on growing, because your linearized equation of state is sigma is 1 minus gamma. Of course, when gamma gets too big, you're in trouble. So you need some cutoff. You need some nonlinearity, especially when you're heading towards CMC. You shouldn't use the linear situation.
Then the second question: if when you have the micelles, so you have a diffusion of the monomers in the filament of the micelles, is the ratio of this diffusion constant important? I mean, that the micelles
I don't think
diffuse much slower.
I can't remember. I just suspect in the computations we took them to be the same. But I think that's one of the myriad different choices of fixing something that I didn't do, or we didn't do. You're certainly right that there is a mobility difference between. Clearly there's a mobility difference between one of them's 100 times bigger than the other.
What about the bulges that you saw in your experiment at the end of the fingers?
Yes. So in fact, these are actually slightly larger. Is this what you're talking about?
Yeah, the bulges in the experiment were 5 times as wide as the fingers.
Oh, yes.
Yeah. No, back one. There.
These ones?
Yeah, those were on the upper right.
Oh, these ones. Oh, this is yeah. So you mean this is a finger which is then broken up into many? Oh, you mean?
I mean, isn't there like a
And
drop
the drop
at the end
yeah.
of bulges at the end of the fingers?
Oh, so you mean
Inside.
The most inside, the longest fingers
Those
seem to have been like slowed down, and then more things are pumped into them.
Yes, yeah, I think so. Yeah, sorry, but I think I just couldn't take my computations a lot far enough to see them. I think if I really, if I was able to get my computations to run more reliably for longer, I think I would start seeing them. Yeah.
So it's a very challenging numerical problem too.
Yeah, so there are people who, it turns out that this nonlinear H equation is in image processing. It appears all over the place. So there are people who spend their lives trying to do that H equation.
It doesn't have as many fluxes in it as yours does.
No, that's true.
So I lost track of the time dependence of the growth rates and linear stability. Do they saturate at constant growth rates?
No, no, they keep. Oh, I see what you mean. You mean does the e to the lambda t is lambda tend to a constant?
Right.
Yes, it does.
We've got 3 more questions. Thank you, Richard.